all the students for the BEE external examination. If you are just going through the third unit, so we got the transformers where EMF equation, working principle, simple problems on substitution of EMF equation formula E is equal to 4.44 F into magnetic flux into N. And thereafter, we have already taken concept called shifting the resistances and reactances. The transformer has got primary and secondary winding. So secondary winding resistance or reactance can be shifted towards the primary winding. Now in this slide, you are able to see total reactance in simple words. What is X2 dash? X2 dash is the reactance which has brought from secondary winding to the primary winding. So when it is shifted from secondary to primary, X2 has become the X2 dash, where X2 dash equal to X2 by K square. So why we are getting divided by K square? We have taken last video which I uploaded. There we have mentioned. So X01 or X1E based upon the textbook notation. So it is the total reactance referred to primary X01, which is a combination of X1 primary winding reactance plus X2 dash. Equivalent reactance referred to the primary. Similarly, the primary winding reactance can be brought to the secondary, then it becomes X1 dash. So here we do get X1 dash equal to K square into X1. You have to remember for transformer, K is equal to transformer turns ratio, N2 by N1 equal to V2 by V1 or E2 by E1 equal to I1 by I2 equal to K. Whenever transformer is a constant flux, constant power machine, whenever voltage increases, the value of current starts to decreases. Therefore, overall power remains constant. So similarly, for this one, in the last video, we have done the problem also based upon this one. So for resistances also, if you see what is R01 or R1E is a combination of R1 primary winding resistance plus equivalent resistance referred to primary, which is R2 dash equal to R2 by K square. Okay, similarly, R02 is equal to secondary winding resistance plus R1 dash K square into R2. Now, this particular class, we are going to concentrate on the efficiency and problems on efficiency. So in order to understand the efficiency, you must know this particular formula, similarly for the impedance. So let me share this slide. So losses in a transformer is a simple question. We got core losses, copper losses, hysteresis loss. The formula you are supposed to remember as per the syllabus here. So eddy current loss, still explanation I've given in the last video, you can check. Copper losses and constant losses are core losses. Copper losses are variable losses. So here, if you substitute the formula, this formula also is very much important. I1 square into R01 equal to I2 square into R02. By substituting the value of R2 dash, we obtain this formula. So let us start the derivation of the efficiency. Let me share the one. So all the students, so efficiency is output by input, output power by input power. For every machine, if the machine is ideal, no losses. Okay. So what is ideal transformer? Ideal transformer is not existing in nature. Ideal transformer efficiency is 100%, losses are equal to 0 and its resistance is also equal to 0. We are using the practical transformers. So input is equal to output plus losses, and output can be written as input minus losses. Now let us see in what way we derive the efficiency derivation as well as condition for maximum efficiency. Efficiency formula we know. So output can be written as input minus losses. You can see here output power can be taken as input power minus losses. So what is the input power applied to the transformer? VI cos theta, which is also called as the rating. What is the word rating means? Power applied to the transformer. So VI cos theta can be written. So what are losses? Losses WI also we can write here. PI we have mentioned. loss equal to iron loss plus copper loss. Copper loss are variable losses as changes in the load. Copper loss also changes. Similarly, iron loss are constant loss, which are eddy current loss and hysteresis loss. Now, we can put the formula of the loss. Loss is equal to Pi plus PCU or Wi plus WC. Efficiency, explain efficiency you will get. Okay, or the problem. Every statement you have write. So input power minus, in the place of losses we can put iron loss plus copper loss. Denominator remains same. Now input power is nothing but the rating. So now what is input power? As I mentioned, primary windings V1, I1, applied voltage and applied current. So input power in watts can be written as the VI cos theta. Cos theta explains the power factor, quality of power transfer from source to load. Okay. So efficiency formula is yes, VI V1 I1 cos theta. No. So V1 I1 cos theta we can also call as the VA rating. VA rating. So what is the formula for efficiency? Means directly you can write VI cos theta minus losses by input. So copper losses, yes, this is important. So iron losses WPI and copper losses PCU. Okay. So PCU is copper loss. I can write I1 square into R1 for primary winding, I2 square into R2 for secondary winding. But usually in order to make the equation simple, we can say copper loss equal to I1 square or I square or I2 square into your I1 square into R01. What is R01? Total resistance referred to primary. R01 equal to R1 plus R2 dash. Okay. Right. We can calculate R1 plus R2 dash. So in the place of PCU, you can use this particular formula. Now, yes, just now we have substituted efficiency formula. Now we are deriving the expression for maximum efficiency. So how we derive, you see, examination also you will get the derivation. Condition for maximum efficiency, remember, copper loss is equal to iron loss. That is the answer actually, that is a proof. If maximum efficiency of a transformer is constant losses equal to variable losses or copper loss is equal to iron loss. So for maxima or minima in mathematics, what we have studied, differentiate the quantity and equate to 0. dn by d theta. You have to differentiate with respect to theta and it is equated to 0. So efficiency we have taken. Condition for maximum efficiency you will get in the examination or explain regarding efficiency. All these things you have to write, then we'll take the problem. So just separating the terms in order to make the derivation in the simple terms. Yes. So now what we can get, 1 minus expression efficiency is equal to just practice this particular value. It's I1 square one minus this expression we are having. Let us differentiate here. Just put I1 and equate to 0. Let us see the derivation here. dn by di1 constant 0. Let me type the expression. V1 1 cos theta. So you can say what is a formula for copper losses? I square into R in general. So Pi or Wi equal to iron losses equal to copper losses. This is the condition for maximum efficiency. Okay. Let me share. Now efficiency formula, you have taken the condition for maximum efficiency. Let us take the problem on efficiency. Okay. So remember, this is also one simple formula, I1 square into R01 equal to I2 square into R02. In few books it has written 1E or R01 or R02. Now, so as I mentioned, remember the formula efficiency just now we have done. As I mentioned, VA rating means it is VI cos theta. VA rating is just VA into cos theta by VA rating into cos theta plus iron losses plus copper losses. Instead of writing WCU or PCU, we can write I1 square into R01 or I2 square into R02. Okay, refer to primary or secondary. So I2. Now efficiency, this is the formula for efficiency at full load. What is full load? In your house, let us say you are turning on all the components. All the components are on, it is full load. If you are saying that, sir, I am not using the 50% of my components in my house, so then the load is off load. So efficiency formula changes with the load. So in the books, they will give you full load. Calculate the efficiency at full load means this formula you are going to write. And calculate the efficiency of off load means we got one fraction n. N is equal to actual load by full load. So if I am saying 50% of the load is used, 50% means 1 by 2. So 1 by 2 by 1. So what is the fractional value of n? N is 0.5. Okay. So now we'll see copper losses will be changing with respect to the changes in load. So what is the formula for copper loss? So you see the new copper loss at any load equal to n square into copper loss at full load. Let us say copper loss at full load is 100 and copper loss at 50% load you have to calculate. So what is 50% load? N is equal to 50%. That is 50% means 1 by 2 by full load. Full load value is always 1 equal to 0.5. 0.5 whole square into full load, copper loss at value. So remember this n value and this copper loss formula, n square into copper loss at full load. So now this formula, so efficiency problem you will get 100%. So what is this efficiency formula? Efficiency equal to VA rating into cos theta by VA rating into cos theta plus PI, that is iron loss, plus copper loss we have taken, a copper loss at full load. I will show you this formula once again. This is a copper loss. We can write I square R or any value copper loss. Depending upon the problem, we are supposed to change. But here, efficiency at any load, this formula is important. Efficiency at any load equal to fractional value small n, n into VA rating into cos theta by VA rating into cos theta. VA rating means voltage into current value, which is mentioned in the problem. N square into copper losses at full load. So remember this formula. Now we'll take the, so how we got this formula? It is based upon just now we have done the derivation, output power by input power. So input is equal to output plus losses. This is the input, input by input plus losses. Percentage efficiency is 100. Now you see all of you. You listen carefully because these problems are tough and you will get for the 15 marks. 3300 by 110, 50 or 60 kVA. This is the power rating, VA rating. 60 kVA means we write 60 into 1000. Single phase and iron losses of 60 watts, primary and secondary winding resistance R1 and R2, they have determined the efficiency on full load, they will mention. So first write the given quantities, kVA as it is. Power factor, they are mentioned lagging. Lagging means inductive load is connected. Leading means capacitive load is connected. Unity power factor means bulb resistive load is connected. So cos theta is equal to 0.8. So first we can calculate for every problem I1 at full load. As I mentioned, full load means they are connecting maximum load to the transformer. Okay, full load. The full load condition represents the maximum current flow through the transformer. Now, what is the current formula? I is equal to P is equal to V into I. So from that, power means not only VI cos theta. Here the transformer rating is in kVA because voltage depends on core losses and current depends on copper losses. Transformer rating is in kVA. See, any object which consumes the energy, its power rating is given in watts. Transformer will not use the energy or consume. It will transfer from one circuit to another circuit. That's why its rating is in volt ampere. It can be K, it can be mega, high level transformers. So I is equal to P by V. We know the formula P is equal to V into I. So I is equal to P by V. So what is the power rating? 60 by V1. So we'll get I1, current flowing through the primary winding current. Next. So primary winding copper losses, I1 square into R1 you can do. I2 similarly, I2 equal to P by V2. P is the VA rating given, 60 VA rating, you will get this one. Secondary copper losses, I2 square into R2, that's okay. So total copper loss equal to I1 square into R1 plus I2 square into R2, this is the value you are going to get. Okay, now, so efficiency at full load. Now this formula is important. Efficiency at full load equal to VA rating we can write, or directly in the problem they are given kVA. You can write that one. Okay, VA rating into cos theta by VA rating into cos theta plus iron loss plus copper loss. Okay, so what is VA rating given in the problem? 60,000. 60 kVA, no, 60,000 into power factor. Substitution, you will get this value. Into 100 you have to do whatever the answer you are getting. Now this is okay, this problem. Now second problem is what the new concept. All of you will try many problems, JN to repeated problems also, but practice with the model. 15 marks you will get the problem. So a 4 kVA. So what is the VA rating? 4 into 1000 power rating. 200 by 400 volts, 50 hertz single phase as an equivalent resistance referred to primary. As I mentioned, every problem they will not give you primary winding resistance, secondary winding resistance. They say directly resistance referred to the primary. That is equivalent resistance referred to primary means R01 value is given 0.15 directly. R01 equal to R1 plus R2 dash, where R2 dash equal to R2 by K square. Okay. Now what is K? E2 by E1. Calculate total copper loss on full load, efficiency, full load at 0.9 power factor lagging. What are the value they are giving? We have to take 0.9 power factor lagging, or next bit is 0.8 power factor leading. Okay, so when you are calculating for efficiency, lagging, leading, no need to take into consideration, just substitute what are the values. We will take the problem on regulation also. There we are supposed to take leading represents negative there, right? So iron losses assume 60 watts. Always iron losses are constant losses. So carefully you must practice this model, understand the question. Number of times you can practice. Okay. So first calculate, right, the given quantities R1E or R01 as I mentioned. K we can calculate. Okay. R02 equal to K square into R01. Just now I mentioned, remember this formula. Okay. Direct shortcut formula, this one. R01 equal to R02 equal to K square into R01. Remember this one. Now, so similarly you are going to calculate I2. Now it is rating is 4010. Total copper losses on full load. Now R1, R2 is not given. So total copper losses on full load. Okay. You can write only I2 square into R02. So total copper losses will, no need to add R01 plus R02. That is not there. So as the resistance referred to primary or secondary, copper losses equal to, we have taken I2 current. You can also calculate I1. Okay. Here by default I2 we have taken. So what will be the formula? Copper losses, entire copper losses, I2 square into R02. R02 we have calculated here, we get 60 watts. In this problem, the copper losses is 60 watts and iron loss is 60 watts. Okay. So problem to problem, the values will get changed. Now, what is the first bit? Copper losses we have done. Efficiency. Now all of you, the second bit is calculate the efficiency at full load with 0.9 lagging. So 0.9 value is important. So efficiency at full load formula is what? Remember this formula, all of you must prepare for the examination this content. Efficiency equal to VA rating into cos theta by VA rating into cos theta plus iron loss plus copper loss at full load. Okay. How to calculate copper loss at full load? Formula is I1 square into R01 or I2 square into R02 or I1 square into R1 plus I2 square into R2. Anything you can use. Okay. Depending upon the requirement. Now, previous problem they have given R1 and R2. Now here R01 they have given, you have taken directly. So VA rating means kVA which is given 4 into 10 power 3, 4 kVA given now into power factor of this bit. Okay, what are the load? 4 into 10 power 3, substitute iron loss plus copper loss, you are going to get the 96%. As the load increases, efficiency increases with load. 96.77. Transformer efficient, transformer is static device, efficiency will be high, 95 to 99. Now let us take the third bit. Okay. And there is no direct textbook for the BW. We have to collect the information unit to unit from different standard textbooks. Okay. Cos theta is equal. What is the third bit? Calculate the efficiency when the power factor is 0.8 and the load is off load. That means the people are using 50% of the devices are only on. We can also give 3 by 4. 3 by 4, if the load is 3 by 4, what you will do? N is equal to, small n is equal to 3 by 4 by 1, which is equal to 3 by 4. Okay, 75% load, 75 by 100. 80% load, 80 by 100. So copper losses at off load, as I mentioned, new load means you must use the formula. Copper losses are variable losses, they change with the changes in load. Copper loss at full load initial we have calculated 60 watts. Okay. Now copper loss at off load is how much? Formula N square into copper loss at full load, 0.5 whole square into 60. Now the copper loss starts to decrease. So now what is the new formula of efficiency at any load? Efficiency at any load equal to N into VA rating into cos theta by N into VA rating cos theta plus iron loss plus copper losses at full load, at new load. Here we have tried copper loss at new load. What is a new load? Off load here. Okay, don't forget it. If it is they are asking for full load, you will write directly copper loss at full load. Copper loss at new load, you must use here indication and then substitute. So direct substitution. N is which load? 50% load, 0.5. 0.5 into 4 into 10 power 3 into this particular substitution. So you can see as the load increases, the efficiency increases. Okay. So condition for maximum efficiency, just now we have done the derivation. Follow that derivation. Okay, you will get that one. So let me take you to the different set of problems. Saving of copper. Auto transformer also video we have released. Very important. Auto transformer. Single winding transformer. So now problems which I have given in one material, star and delta. Only first two problems are there for you as per the syllabus. Okay. So please communicate every time these 2 days. So any problem on the transformer is just formula substitution, but problems on losses are important. See here you see, this is the direct problem. A 500 kVA transformer has iron loss, WI or PI equal to 2 kilowatts. Full load copper loss is 5 kilowatts. As copper loss WCU or PCU. Efficiency they have given of full load. And cos theta they are mentioning 1. Okay. Efficiency 75%, 75 by 100. Okay, 75% means. So cos theta is 1. Now, how to solve it is direct indication. Entire thing they have given. Definitely, this problem was last year for the 8 marks. Okay, so the efficiency equal to 75 by 75 by 100.75. Copper losses efficiency at any load. They have mentioned, they are not asking you to calculate at Full load. Calculate the efficiency at 75% of full load. Understood, all of you? Calculate the efficiency at 75% of full load. So directly, efficiency at any load formula is what you have to remember this one. N into VA rating by N into VA rating plus iron loss plus N square into copper losses at plus you can write here copper loss at any load. So you can directly substitute here. We know copper loss at new load equal to N square into copper loss at full load. So N is equal to how much? 0.75. 0.75 whole square into copper loss at full load. What is the copper loss at full load? They have given copper loss, they have given in the problem 5 kilowatts. Okay. Iron loss will remain constant always. So directly you can write here 5 kilowatts, 5000. Okay. You can substitute or you can write the form directly. So you'll get the value. So these type of problems are direct problems. So you can see here this particular problem. This is regulation one. So regulation I take separately, don't get confused. So area of cross section, primary and secondary windings. You can see whenever any problem on transformer, you can see these are complicated one. Generally will not be given for you this problem. I am saying iron loss of 100 kVA. What is the VA rating? 100 into 1000. 1000 by 250 single phase transformer is iron loss is 1000. Copper loss when primary carries a current of 50 amperes is 500 watts. So I1 current is given and copper loss is how much? 500 watt. Area of cross section. So whenever they are asking area of cross section or anything, you know the transformer formula. What is the transformer formula? EMF equation. E is equal to 4.44 F into magnetic flux into N1. So N1 you can calculate easily, point T. Okay. 0.9 tons and as a primary as 100 tons. Magnetic flux density, this one 0.9. So directly you can substitute your magnetic field intensity is equal to 0.9 into T. So K you can take for every V2 by V1 or E2 by E1. So we can calculate V1. We'll get magnetic flux density. That bit is finished. So similarly you calculate I1 and I2. I2 equal to P by V2. So no need of these conditions. So now let us take this one. So efficiency at which load they are asking, you have to calculate that one. This is a full load, that's why directly we can write the power. Now let us try this one. So practice, feel these problems on efficiency. Definitely you will get a single phase 100 kVA, 50 Hz transformer 85%, as 89.5% efficiency at 0.8 power for both at full load and also at off load. 2 bits we have to do. Efficiency of transformer at 75%. No need to get. So first efficiency at any load formula, we know N into VA rating into cos theta by N into VA rating cos theta plus copper loss plus here the formula is copper losses at new load. Copper loss at new load. What is the formula for copper loss at any load? Copper loss at any load equal to small n, N square into copper loss at full load. So N, iron loss, full load copper loss. So first, for how many loads we have to do? They have given off load and full load and this one. Determine the efficiency of the transformer at 75% of full load. Load means, okay. So first, let us calculate the full load. N is equal to 1. That is for the full load. So your direct substitution we can do. So no need to go for this one. So I've just taken for you people. They are going to ask you only the simple problems based upon the efficiency. So first 2 problems what we have taken, be thorough with that procedure. So let us take the last one, this one. A 50 kVA transformer has iron loss, resistance, low voltage, high voltage windings. Okay. So primary and secondary can be called as low as well as high depending upon the year. High voltage winding. High voltage winding will be primary because it is primary winding voltage is high. The low calculated efficiency on full load and off load. So first in this problem, what they have given, resistance, low voltage, high voltage they have given. Okay, so you can convert the resistances to primary. So resistance referred to primary, R01 equal to, so what is resistance? Primary winding R1, R2 they have given. You can directly use the syntax, but this is the standard method. Convert this resistance to R02 or R01. R01 I am converting, R1 plus R2 dash, substitute, any problem. Even the first problem we have done R1 square, separately we have calculated losses. So any problem can, if they are giving both resistance also, you can convert them to one resistance, total resistance R01 using this formula. So then we'll get I1. Okay, or I2 you can calculate. So copper loss is equal to I1 square into R01 or I2 square into R02. Copper losses at full load you got. Now first bit copper efficiency at full load you can directly substitute. Okay, so this direct substitution problems only will be asked. Only formula you have to remember: copper loss at full load and off load. It becomes easy because the previous papers also the direct problems. Offload efficiency at offload equal to N into VA rating into cos theta by N into VA rating cos theta plus iron loss plus N square into copper loss at full load, or you can write copper loss at new load and separately you can solve. So N square here you are going to substitute 97.89. Always full load will have the maximum efficiency. So this is regarding the efficiency problems and the condition for maximum efficiency. Thank you.